Okay, here everything we have written in terms of omega, but the same thing can be written in terms of f also. So either delta omega equal to omega naught by QE, or I can also write delta f is equal to f naught by QE. In general, I can summarize the uh, relation between quality factor, bandwidth, and resonant frequency. Bandwidth equal to f naught by quality factor, or quality factor equal to f naught by bandwidth. Whatever way it is easy to remember for you, you can do that. So delta omega equal to omega naught by QE. And you know the formula for QE. QE is for a parallel circuit. So for parallel circuit, the formula for quality factor is R by X. So either you can write R by omega naught L, or it is R by 1 by omega naught C, or omega naught C into R. So either any one of the thing you can write. So substitute the first expression QE equal to omega naught C into RT in the delta omega expression. So delta omega will be equal to omega naught divided by omega naught C into R. I can cancel out this omega naught, so it is 1 by RT into C. So F will be 1 by 2 pi RT into C. So the bandwidth is going to depend on RT and C. If you take the second expression, it will depend on RT and L. Okay, so we have taken the first expression, so we can say the bandwidth is going to be 1 by RT into C. See here, it is radians per second. So if we convert into frequency, F will be 1 by 2 pi RT into C hertz. Okay, so if you plot the response of a tuned amplifier, yes, any doubt? Okay, so if you plot the response of a tuned amplifier, you can see at one particular frequency you get peak response and it starts falling away as the frequency is away. So at this particular frequency is center frequency not, and the value of delta at f naught is going to be 0. Okay, the value of delta at f naught is going to be 0. That's why they have plotted in terms of delta. You can even plot in terms of frequency. So this is what is the graph we got in our labs, right, for a tuned amplifier. So one particular frequency I have maximum response. That frequency is given by the frequency, resonant frequency, f naught. And when the quality factor is going to increase, my bandwidth will decrease. You see Q is equal to 5, the graph is broader. When you make Q is equal to 10, the graph becomes narrow. So we have seen Q is equal to f naught by bandwidth. So when I'm going to increase my quality factor, my bandwidth will reduce, keeping f naught constant because I'm not changing any circuit parameters. Okay. So this is going to be the frequency response graph for a single tuned amplifier. At the resonant frequency, the circuit is going to act like a pure resistor. At f naught, it is going to be R. Below f naught, it is going to be L. Above f naught, it is going to be acting like a capacitance. Okay, it is going to act like a capacitance. Okay, so this is going to be the complete derivation of single tuned amplifier. I want to take it in a complete one class because if we split and take, flow will be completely lost. So we have studied today what is a small signal tuned amplifier, what are the different types of tuned amplifiers. We have taken capacitively coupled single tuned amplifier as our uh, topic for discussion today, and we have drawn the circuit for that. We have replaced the transistor by hybrid pi model because high frequency operation and simplification of circuit, then finding out the impedance, output voltage, then input voltage, then finding out the gain. Once you find out the gain, we are finding out the bandwidth directly by making the substitution. The ratio is going to be 1 by root 2. Okay, we are doing that, and finally we got the bandwidth as omega naught by QE, or in terms of RT, you say it is 1 by RT into capital C. And finally, the frequency response graph for your single tune amplifier. So this will complete the derivation for a single tune amplifier. This will complete the And you have to end the answer for singleton amplifier with the frequency response graph.